Hello and welcome to part 3 in this series on rectangular waveguides. In this video we'll calculate HZ for the TE or transverse electric mode. This is a little bit more complicated than for the TM mode. The value of HZ won't be 0 at the walls like EZ, so we'll have to try something a bit different. HZ won't be 0 at the walls because the magnetic response is too slow for a microwave. EZ will be set to be 0 and HZ will have to be calculated using this fact. So this is EX as a function of HZ and EZ. It is an equation that we'll calculate later in the series, but we'll need to use it now. We know that EZ is 0 and we can substitute this in. So then we're left with EX being a linear function of this derivative HZ. This derivative of HZ is proportional to EX. We know that EX is 0 at the walls. So this derivative of HZ is also equal to 0 at the walls because it is proportional to EX. You can see on this diagram that EX is equal to 0. And it shows the direction EX is in if it isn't 0. Then you can see HZ and its direction. The derivative of HZ with respect to Y can be seen from this sample of HZ curves as they rise as a function of Y in the waveguide. You can see that the derivative of HZ with respect to Y is 0, and it looks like it is proportional to the sine of Y. Since this makes this derivative 0 at the walls, and the function needs to be a sinusoid function. But we still have to prove it more formally. Now we have to find the function of HZ as it goes across the waveguide as a function of x. We can use this equation here, which we'll derive later, but need to use now. This calculation is similar to the last one. Since EZ is 0, being TE mode, we can substitute the 0 in here. Then we'll have this equation. So EY is equal to an expression multiplied by this derivative of HZ. And so we can write down that EY is proportional to this derivative of HZ. Since EY is 0 at the walls, then the derivative of HZ with respect to x is also 0 at the walls. Looking at the diagram where EY and HZ are, showing their directions when they aren't equal to 0, we can see that the derivative of HZ with respect to x is also 0 at the walls, and so HZ is a cosine function of x, which we'll have to show later more formally. In this mode, EZ will be 0 because E is transverse to its direction of propagation, so HZ will need to be calculated. HZ will be solved in the x direction by standing waves, but HZ won't be 0 at the walls, so the waves of HZ won't look like this picture. These waves are of the derivative of HZ with respect to x. But EY will be proportional to the derivative of h with respect to x. So this partial derivative quantity will be 0 when x is equal to 0 at the left-hand wall of the waveguide. And so this quantity will be equal to this sine function. This quantity will also be 0 when x is equal to a at the right-hand wall. Substituting these values into the sine function gives us this equation. This equation is solved to be this, with an integer m being equal to all positive and 0 integers. Then kx will be solved to be this. And so this partial derivative will be equal to this. We can now start to solve this equation in the y direction, being the up and down direction. This partial differential quantity must be 0 at the bottom wall when y is equal to 0, and it is found to be equal to this sine function. This quantity is also found to be 0 at the top wall when y is equal to b. Substituting all of these values in gives us this equation, which can be solved to be this equation, where an integer n is introduced to be equal to these numbers, so multiple values may be found. Ky is found to be this, so there are multiple values of ky. And so this is what this quantity is equal to. We now have these three expressions that we have to put together to find HZ. These derivatives of HZ will be equal to these expressions when HZ is equal to this expression. We know that HZ has to solve the wave equation, so it must be a sinusoid function of x. So it must be a cosine function of x, because its derivative with respect to x must be 0 at the walls, and similarly for y. Now to find which modes exist for the TE mode, that is, which values of n and m can TE exist for. HZ should exist for m is equal to 0. Substituting m is equal to 0 into the expression for HZ gives us this expression, which gives us a cosine 0 term, which gives us 1 multiplied by a lot of expressions, which gives us this expression, which looks like it could exist in the waveguide. Now to check if HZ can exist for n is equal to 0. Substituting n is equal to 0 into the expression for HZ gives us this expression, which gives us this cosine of 0 term, which gives us a lot of terms multiplied by 1, and which gives us this term which could exist in the waveguide. Now to see whether the mode can exist for both m and n being 0. Substituting these values into the expression for HZ gives us this equation, which gives us 2 cosine 0 terms, which gives us 2 expressions multiplied by 2 ones, which gives us this expression. Both of these partial derivatives of HZ are equal to 0. We already know that EZ is 0 because the waveguide is in TE mode. We can calculate EX using this equation that we'll derive later and have already used in this video. Substituting these values in gives us this equation, which gives us EX equals 0, and EY can be found to be 0 in a similar way. So the electric field is 0 everywhere in the waveguide. So the TE mode can't exist for both n and m being 0 together. We can write this mode out as TE with 2 0 subscripts at the bottom, saying that it doesn't exist.